Hi, in this video, we're going to talk about using the product rule and the chain rule simultaneously. So let's look at an example. Here I have a function f of x is defined as a product of two functions. The first function in the product is x squared. The second function in the product is x squared plus 1 to the 7th. Now the second function is a composition of x squared plus 1 and then raising that to the 7th. So we have not only the product rule to use, but the chain rule. Now, which do we use first? We're going to use the product rule first because the last thing that you do in evaluating this function is taking the product of these two functions. So it's kind of the last thing out is the first thing you attack. And the last thing we do is take products, so the first thing we'll do is use the product rule. So f prime of x is going to be the derivative of the first function, which is 2x, times the second function left alone, x squared plus 1 to the 7th, plus, now we leave x squared alone, the first function alone, and differentiate the second. Now when differentiating the second, we have to use the chain rule. The inside function is x squared plus 1, the outside function is u to the 7th. Let's take the derivative of the outside function, that'll be 7 times x squared plus 1 to the 6th by the power rule. Okay, we reduce the exponent by 1 and put the old exponent in front. But then we have to differentiate the inside by the chain rule. The derivative of x squared plus 1 is 2x. Okay, so that's it. You can simplify a little bit. The first term doesn't admit much simplification, but the second term, we can bring the 2x to the front, and we can multiply the 2 by 7 and get 14, and the x gets multiplied by x squared to get x cubed, and then we have an x squared plus 1 to the 6th. So that's basically it. Let's look at now another example. In this example, I have y equals the square root of t squared plus 1 times e to the t, and I'm asked to find dy dt. Again, I have a product, but within the first function, I have a composition. The inside function is t squared plus 1, the second function is the square root. Okay, so dy dt, I'm going to use the product rule first, because the last thing I do in evaluating this expression is multiply the evaluation of the square root times the e to the t. But when differentiating this first function, I have to use the chain rule. Notice that first function is the same as t squared plus 1 to the 1/2, which allows me to use the power rule to differentiate the outside function. The derivative of this is 1/2 t squared plus 1. Then I have to reduce the exponent by 1, so 1/2 minus 1 is going to be minus 1/2. But then I have to differentiate the inside function. The inside function is t squared plus 1. The derivative of t squared plus 1 is 2t. Okay, so that's the derivative of just the first part of my product. Then I have to multiply by the second term in my product, which is e to the t. This is f prime times g. Now I have to take the first term in my product, t squared plus 1, and multiply it by the derivative e to the t. Well, the derivative e to the t is simply e to the t. And that's it. I could simplify a little bit by noticing that the 2 times the 1/2 will give me just 1, so they cancel. And I can rewrite this as t squared plus 1 to the minus 1/2 times e to the t plus t squared plus 1 to e to the t. If I want to rewrite everything in terms of square roots, then this quantity to the minus 1/2 is the same as 1 over, because of the minus sign, and then the square root of t squared plus 1 times e to the t. That's just algebra. As derivatives, all these are equivalent. Okay, one more example using chain rule and product rule. Here it is, s to the 5th times 7 to the 3s squared minus 7, minus s, excuse me. So Again, we have a product, s to the fifth times this. And the last thing we do in evaluating this expression is evaluating the product. So we're going to use the product rule first. The product rule says I'm going to take the derivative of the first function. That's going to be the same as 5 times s to the fourth by the power rule. Then I'll have to multiply by the second function without doing anything to it. And then I have to take the first function, s to the fifth, multiply it by the derivative of the second function. Now here's where the chain rule needs to be applied, because this is a composition of 7 to the u, where u is 3s squared minus s. So what is the derivative of 7 to the u? Well, that's the same as 7 to the u times ln of 7. In this case, u is 3s squared minus s, so then I have to multiply by ln of 7. But in using the chain rule, I still have to differentiate by the inside. Differentiate the inside function, which is going to be 2 times 3, which is 6s minus 1. 6s minus 1. Okay, so that's a big long product. Again, this came from differentiating the outside function, the 7 to the u. The derivative of 7 to the u is simply 7 to the u times ln of 7, and that's what's written here. But then I have to differentiate the u part, which is the derivative of 3s squared minus s, which is 6s minus 1 by the power rule. Okay, so altogether, this is it. That's all I need to do. If I want to clean it up a little bit, I still have 5s to the fourth times 7 3s squared minus s plus, and then I can put the s to the fifth here, and I can bring the 6s minus 1, makes it look a little nicer, times ln of 7, and then I have the very last thing is this 3s squared minus s. But it's equivalent to the other ones. These are both the same.